400 degrees Celsius. Okay, so of course, when you're solving this type of question, I mentioned, first thing you need to identify what kind of system. Of course, for now you have only learned closed system lah, so obviously this is going to be a closed system. So this will be the clue to closed system. Piston cylinder device is a closed system. Then you need to note that you are dealing with steam. So you are dealing with H2O here, meaning when you solve this question, you need to use the thermodynamics properties table for water. Okay. Now, and then you note down what are the states that are given to you. So let's get myself some space here. Now, so you are told that initially, so at state 1, P1 is 1 megapascal and T1 is 400 degrees Celsius. Okay, so when you see this, right, this is kind of one type of clue. It is of course not always the case, but we know that under saturated state, temperature and pressure are dependent, right? So if meaning they won't change, like one won't change without the other not changing. So if you see the question giving you both of these properties and information, it usually means that this is either a compressed liquid or superheated steam. Which in this case, this should be a superheated steam superheated water. Okay, then the location of the stops corresponds to 40% of the initial volume. So we have a pair of stops here. So what do? Basically, they will stop the cylinder. The piston. They will stop the piston when it moves, when it reaches that location. And you are told that this location here is 40% of the volume, or meaning 0.4 of the initial volume. So now the steam is cooled. So you have Q out. Determine the compression work. If the final state is 1 megapascal and 250 degrees Celsius, so that would actually be your state 2. Okay, 1 megapascal. Okay, it refused to write, but whatever lah. Okay, stop. So P2 is 1 megapascal, T2 is 250 degrees Celsius. That's your second state. Of course, then B, you actually have a third state when the pressure is 500 kilopascal. And C, temperature at the final state, part B. So meaning we are looking for T3. So you have 3 states here, 2 processes. Or technically 1 process, but you can split into 2 lah. So we imagine that we have 2 processes, 3 different states. So you can see a description as well. A piston cylinder device with a set of stops contains steam at a specified state. Now the steam is cooled. The compression work for 2 cases and the final temperature are to be determined. Okay, so we look at A first. So A actually is pretty straightforward. You can see that it is actually an isobaric process, right? Because the pressure doesn't change. So basically, it changed from 1 megapascal 400 degrees Celsius to 1 megapascal 250 degrees Celsius. You are asked to find the compression work, which means you are actually looking for the boundary work, right? So in order to find boundary work, what information do you need to find based on these 2 properties? No. What's the equation for boundary work? PdV. So meaning here what you need would be the specific volume. Okay, you have the initial mass, you want the specific volume. So we look at A first, you ignore the bottom part. So the specific volumes are the information that you need. So based on the first state and the second state, so both of them you are given the pressure and temperature. So if you go to the properties table, I'll just show you one time. Okay. So if you go to the properties table, for water, now So we can refer to the pressure table. Technically speaking, you can refer to the temperature table as well, but since both states are at pressure, we can just check it in one shot. So 1 megapascal, saturated temperature is 179.88. So in this case, both of the temperatures are above the saturated temperature, right? So since they are both above the saturated temperature, which means that both of these are in superheated state. So if they are in superheated state, then you go to the superheated table, look for pressure and temperature, look for the specific volume. So once you found the specific volume, so for these two are the values, then boundary work, since this is an isobaric process, a constant pressure process, then boundary work equation is simply mass multiplied by P delta V. So usually you will have an integral, but here since P is a constant, then there's no, you can take out the integral. It is just a linear process. So actually it's just, if you know, on PV diagram, we learned that PV diagram, area under the graph is the boundary work, right? So in this case, since P is a constant, so yeah, all you need to find is this, which is that equation. Of course, this diagram is not correct because it is missing the saturated line. The saturation line, sorry, not saturated line. So part A, can everyone understand? Okay, if you understand part A, now part B will be slightly more complicated. Okay, so part B, what is given in the question is that, let's look back. You are told that now pressure is 500 kilopascal when the piston is resting on the stop, right? So meaning in state 3, P3 is 500 kilopascal. What else do we know? We know that the piston is resting on the stop. What can you gather from this information? Actually, to be fair, at this point, P3 is 500 kilopascal, doesn't really help you. But what else? So we know that the piston stops resting on the stop, right? What does that tell you?
Joe, can you show me how you get a 0.3061? Because you check it in the pressure table, right?
I think the example is from an older version, I guess. Then maybe slightly different. What's the temperature? 400, right? 0.3061. So the other one is 250, then this one. So sometimes, some example that you come across, right, they might differ very, very slightly. So like for example, let's say this is 0.23275. Yeah, so like ME, if you look, or rather, if you have taken thermo in diploma, the table they gave you was not the same as table, right? So if you check back your old table, if you have it, you will see that it might differ slightly one, like it may be like 2327 without the 5, but they are usually quite close one. So different table will give you different values, so this one bear in mind. Don't try to change table. If you use one, just keep one. Keep at one. Like because sometimes if you feel like lazy, you Google it online. They will give you values also, but sometimes it won't be the same lah. Yeah. Okay, so now we're back to state 3. When the piston is resting on the stop, what you know would be V3 is 0.4 V1. Because meaning when it reaches the stop, the piston will not go down further. right? So V3 equals to 0.4 V1. This is what we know. And since mass is a constant, it also means that V3 is equals to 0.4 V1. Okay, so this is actually the second information that you know about this question. Okay, but for now, we look at B first. So volume of the cylinder at the final state is 40% of initial volume, so it's stated there. Then the boundary work becomes, so you can see that boundary work equation here, right? For some weird reason, we actually use 1000 kilopascal here. So why is that the case? Okay, so here you need to understand how the process works. So you can see that from 1 to 2, as you cool down the steam, pressure doesn't change, right? It just basically volume reduces, it moves. Essentially what happened here is something like this. It doesn't let me draw on this. Okay, it's something like this. So when you cool down the system, then piston will move down. Makes sense, right? When you cool down, volume reduce, so you see it moves down not because of the pressure. Pressure is a constant. It will move because the specific volume reduces. So the piston moves down. But overall, you can see that from the system, there is no external forces compressing on it. Meaning you don't get any extra force. So if there's no extra force, based on dynamics, your net force is still the same. So pressure won't change. Agree on this? Because you don't get, there's no external forces acting on the system. It's just a heat removal. So, and then, so the whole process will be an isobaric process. So the thing is, when it hits the stop, then you get external forces. Because the stop will be, basically will be the one that is acting on the piston. The piston try to move down, but the stop will push it up. In a sense, relatively speaking, of course, it's not going to push it up. So that is how the pressure reduced to 500 kilopascal. Okay, so but then we are still looking for the compression work in B. So the compression work will only happen from 1 megapascal 400 degrees Celsius all the way to when it first rests on the piston. Meaning when it reach the on the piston when it first reach the stop. But after that, then you don't have any boundary work anymore because it won't move. Does that make sense to you? So we still use 1000 kilopascal. Actually better. Why didn't I do that? Actually, it's better for me to illustrate it in terms of PV diagram. Okay. So what happened here is this. Initially, superheated steam, right? So this is state 1. Then it will move isobarically. So state 2 is somewhere here. Now what happened here will be this. To be fair, I don't know when it will stop also. Okay, let's get rid of this saturated line. Because state 3, let me see. Because I don't know what is state 3 for now. Okay, the answer is I don't know when is state 3, so I cannot represent it with the saturated line. So now, so it will move at 2 until here. When it reach the stop, right, the process will become like this. Then it goes to state 3. Does this make sense to you? So it will move isobarically. So the piston will move isobarically. That's why it is a horizontal line. Okay, it will move isobarically until it reaches the stop. Then when it reaches the stop, then it cannot move anymore. But the pressure will reduce because it tries to move down, but the stop is pushing it up. So then the pressure will reduce. That's why it is a straight line down. But then this point, there is no boundary work.
Can you explain why from state 1 to state 2 is going like this instead of going like
you look at V1 of state 1, then you look at V2.
400, 250.
The volume will reduce because you are cooling it down. It is a compressor work. So V, it will go to the left, horizontally. So can everyone understand this PV diagram? So, which is also why, for boundary work at point B, we are still using 1000 kilopascal because this is the area that we are looking at. So, from the moment it hits the stop until state 3, there is no boundary work because the piston stopped moving. Then this is V1. Then this will be V3. So try to digest this first. I jump to part C. Okay, so this is part C. Part C is more straightforward. So at part C, I have just noted down. We know that actually it's supposed to be P3 lah. You say P2 a bit weird, but anyway, because they split it into two different things. Anyway, so part C, we know that pressure is 0.5 megapascal. You know that V3 or V2 is 0.1226. Right, so this one, very straightforward. You just go to the table again. This time you check 500 kilopascal. Actually, you can just check here. So at saturated state, the specific volume, sorry, this one. So at saturated state, specific volume is 0. For VG is 0.37483. Or if this one not so clear to you, just come back here. Again, so 500 kilopascal. We know that VF is 0.001093. VG is 0.37483. The V here that you have is 0.1226. So this V, again, these two we treat them is P3 and V3 in what I thought. So V3 is actually between VG at 500 kilopascal and VF at 500 kilopascal. So we know that this is a saturated mixture. So if you know that it's saturated mixture, meaning the temperature is simply the saturated temperature, which is 151.83. Okay, so part C is actually more straightforward compared to part B. So try to understand B here, or what you don't understand here, you let me know. So always remember, if you do not have, so you in general you don't really need much dynamics knowledge. That dynamic is just what I used to explain to you. But in general, if you don't have any external forces, pressure won't change. This one you need to remember. V3 is between VG and VF, and then saturated, it is a saturated mixture.
And 500.
Sorry, kilopascal, not kilogram.
So 8 and 500. Square root 8 and.
Where do you get square root 8?
Oh, V8.
Where do you get 8?
Oh, what is that?
No, that's a small v. Specific volume. It's not square root. Like I said, because we have too many v here, so all the square, the small f, the small v, I will just write. This one cannot erase.
That one is a A.
So cannot erase. So now cannot write. And where do you get a? At. I have been writing that for weeks. please try to
No,
observe.
I know, it's just very hard to see.
Sorry.
I thought it's a...
This is okay. So again, V, the small v with a horizontal line is specific volume. That's usually how we write in this subject also. Okay, because too many v, we need to differentiate the v that we write. Okay, is everyone clear with this example? Alright, if yes, then I will go to the next example. Okay. Anyone still need this? No, right? Okay, we go to the next example. So, here, now this question is actually slightly different. So, this one will need to make use of the equation that you learned from the boundary work section. So, a piston cylinder device initially contains 0.07 meter cube of nitrogen gas at 130 kilopascal and 120 degrees Celsius. So now we are dealing with nitrogen gas, so you cannot use the H2O table anymore. So the nitrogen is now expanded polytropically to a state of 100 kilopascal and 100 degrees Celsius. Determine the boundary work done during this process. So this question is actually more straightforward. So you are given P1. So P1 is 130 kilopascal. T1 is 120 degrees Celsius. And P2 is 100 kilopascal. T2 is 100 degrees Celsius. You need to find the boundary work. So the keyword here would be polytropically. So if the process is a polytropic process, then let us go all the way back. So if it is a polytropic process, right, then you actually need to make use of this equation. Okay, so let's just look at the answer. Okay, so the issue here would be you probably won't know what are the values that you need for this question here. So now when you look at the answer, because they look for the information based on what they know they need, but for you probably don't know what you need first. So I will start from the back instead when I explain this. So meaning, just now I mentioned we need this equation, right? So we need to use this particular equation. And so when you see this equation, one thing that should come that you need to bear in mind will be actually this, okay? Because this equation is actually derived from this equation. So back then when we do the derivation, it actually comes from that relation. The normal gas relation or normal ideal gas relation will be PV equals to PV. But in this case, it's PV N, because we need the N to differentiate the type of gas. So we come back to this PV minus PV over 1 minus N. So you need the volume of this gas. So since we know that for nitrogen, again, in a way we can still use the ideal gas equation to a certain extent. So we use the ideal gas equation here, which is PV equals to nRT. To look for, what does the question give you? So the question does give you V1. So actually V1 is 0.07 meter cube. Okay, so technically speaking, if you are not big on, actually not really, technically speaking, you don't need this step at all. Because you can just do PV over T equals to PV over T. This will give you the second V. Because R is a constant, M is a constant, right? So it's technically you can just do PV over T equals to PV over T. But this does tell you one very important thing. Maybe for other, for other purposes. So this table, right, there's also a very useful page, which is this page here, where it gives you all the properties of subcommon gases. So that's what this. So here nitrogen, you can see this is where the question gets the gas constant. But of course, like I said, this question you don't really need the gas constant now. You can actually use PV over T equals to PV over T. You can get the volume. Okay, so once you get the volume, then you can use this PVN relation. PVN equals to PVN equation relation to find out what is the N. So meaning that what is the polytropic index for this nitrogen gas here, and from here, then you can just sub the N value in to get the boundary work. So please bear in mind that every single equation that you use here, you cannot use for water, okay? Don't use, even PV over T, don't use this relation for H2O.
So the 273K is, where did you get it?
273K is how you convert that degree Celsius to Kelvin. Okay, again, another thing, this one, we will talk about it in the next section again, but always remember, temperature must convert to Kelvin.
So must always plus.
Yeah, just keep it that way lah. Except for when you read the water table, okay? Because I did have students that really convert everything, including when they read the water table, and then they got the wrong answer. Water table is in degrees Celsius. Okay, so this question, nothing too extreme. It basically just tells you how to use the polytropic expansion or compression equation. But yeah, you need to incorporate ideal gas equation here, because or else you won't have the second volume.
So how you get the N?
How you get the N?
Compare the polytropical index.
Yeah, you just compare these two.
This question
You can move it over to the other side, then combine them as an N, then equals to 1.
Okay?
You can move this over here. So something like this lah. I don't have the full working, so you can do something like this. So then you put together equal 1, right? Yeah, you can do something like this.
This question 是哪一个会选3个会选
know everything inside because I have to remove the N.
So anyway, this one, I think this question you try it out on your own if, when you are free, because yeah, again, the working is actually just this, or I will jump to the next section. Sorry, right? Okay, so today I will finish up this closed system section, hopefully. But either way, we still have time. Okay, let's look at the next section. So next section, we will talk about something that is slightly different now, which is we will look at this thing through internal energy. Through the eyes of ideal gas now. Okay, so that's why the example just now is not so important because we still haven't gone into it yet. Okay, so now when we look at, so here this section we are actually talking about internal energy and specific heats. We actually will talk a little bit about enthalpy as well. So objectives here is to define the specific heat at constant volume and specific heat at constant pressure. Then we will calculate the internal energy, enthalpy, and specific heats of ideal gas, liquids, and solid using derived property relationships. And we will use internal energy, enthalpy, and specific heat relationship to conduct energy analysis of closed system. Okay, so essentially here we will learn about the relationship between specific heats and energy. Okay, so specific heat is something that you have learned before. Is the term C if we are looking at specific heat. So specific heat is the energy required to raise the temperature of a unit mass of a substance by 1 degree, which is also why the unit is kilojoule per kg degree Celsius. So the energy required to raise 1 kg by 1 degree Celsius of a substance. So this is actually so based on this, you can see that the definition is actually, or rather the use of the specific heat is the measure of thermal energy storage capability. So how much energy it can store, a certain body can store. So this you have learned before. The equation that you used to use will be mc delta T, right? So that particular C. So that's what we are learning here. Okay, so different body or different substance will have different specific heat value because they have different capability of storing energy. Basically that, or thermal energy. So last time when you learn mc delta T, we only learn for one C value. So here we actually will have two C values. So again, if you go back to this table, you will see that you actually have a Cp value as well as a Cv value. Okay, so here this is what we will learn how to use this. Okay, so if you look at the left hand side, specific heat at constant volume. So very straightforward. When we say that specific heat at constant volume, Cv, volume, so V. The other side, specific heat at constant pressure, so Cp, because pressure. Okay, now, so when you talk about specific heat at constant volume, logically, you can think about it in terms of a rigid tank, let's say, because volume doesn't change, right? And then, if you talk about constant pressure, remember when we talk about closed system, when you have a constant pressure movement for boundary work, we can move the boundary work over to the right hand side, and then we change the entire thing into enthalpy, right? So we said that U for constant pressure, U plus PV equals to H. So this is related to enthalpy, and this is related to internal energy. So essentially, what we are distilling here is this. So next slide. Q minus W equals to delta U. Now, again, because we are talking about C here, right? So meaning, we are specifically talking about the thermal energy, because that was the definition. Specific heat is a measure of thermal energy storage. So when you derive this, we go back to the closed system equation, Q minus W equals to delta U. So we are only focusing on the Q in this case. So we are assuming a system that only have the change in Q. So for constant volume, Q equals to delta U. So this Q will also be equals to CV delta T. So if it is capital letter, then this MCV delta T lah. But if the small letter, we can take out the M. And for constant pressure, same thing that I mentioned just now, because constant pressure process, you cannot run from the boundary work. So we move the boundary work over to the other side, so it becomes delta H. So same thing. So this will be MCP delta T. And without the M, the small letter one will become CP delta T. So this will be delta H. So, which means when you have CV T or CV delta T, we are talking about the change in internal energy. While when we are talking about CP delta T, we are talking about the change in enthalpy. So, as CV and CP are property relations, they are independent of the type of process. They can be found if given other properties. So this one we don't care about what kind of process it takes place. As long as you have the initial temperature, you have the final temperature, that is the change in internal energy or enthalpy. Okay, so one thing to take note about this is that even though we derive this through constant volume process and constant pressure process, but as long as we are dealing with ideal gas and constant specific, this one later. So as long as we are dealing with ideal gas, right? Whatever process, if you need to find the internal energy, you can always use CP delta T. If you need the enthalpy, you can always use CP delta T. So even if the process is not constant pressure, but you still need to find the change in enthalpy, let's say, you can still use this equation. It doesn't have to be a constant pressure or volume process. We are just using this example here to derive and show you that CV delta T is delta U, CP delta T is delta H, but they are interchangeable for any processes. Okay, so that is what we want to show you here. So again, this is only applicable for ideal gases. So now, this CP and CV value, they can change with temperature, but changes are usually not very large. So, in a lot of the time we will just assume that CV and CP values are constant. Okay, so here again, yeah, we have some derivation here. So one thing that you can see also is that one very interesting thing. We know H equals to U plus PV, right? But from ideal gas equation, we know that PV is equal to RT without the M, because here we are talking about specific volume, small v. So, in certain cases, let's say you need to find this boundary work, you can actually use U plus RT instead. Again, we might have some example that will show you this lah, but this one is just that to show you that PV equals RT. So PV and RT can be interchangeable, but of course again for ideal gas only. Okay, so we have a derivation here that shows that since H equals to U plus PV, and we replace it in terms of, or with this relation that we say here, and then we change, we change delta H and delta U into CP delta T, CV delta T. So from here, delta T can cancel off, delta T can cancel off, delta T can cancel off. We get CP equals to CV plus R. So sometimes you will get this relation in terms of mole, but not too important for your syllabus this semester. You can actually replace the CP with a CP bar, CV with a CP bar, because it's in terms of mole. Then in this case, R becomes RU, which is universal R. It's just one value lah. So if you don't know what's universal constant, gas constant, there's actually a value here. So basically for any gases, if you are using in terms of mole, you can just use this value. But otherwise, when you are dealing with in terms of kg, all the value will be different here. So you can see that R value, CP value, CV value, and K at 300 Kelvin is given in this table here. And we also, so for the K value that you saw just now at the table is what we call specific heat ratio. It's simply CP over CV. Okay, so you can see that we have Cp equals to Cv plus R. We also know that Cp over Cv equals to K, which means that when we are using ideal gas, right, as long as I give you two of these values, you should be able to find the other two. So Cp, Cv, R, and K. Again, these four values in the table lah. So let's say, for example, I need you to use these values. Let's say in exam, if I say that you just use the value at room temperature, then you take values from here. If I give you a specific value, then you use the value that I give you lah, of course. Then let's say if I only give you two, then you need to know how to find the other two lah. Basically that.
The CP bar, what does it mean by CP bar? You change the
Cp in terms of kilomole.
but we won't use it rarely.
Very, very rarely. It's the same thing. The way that you use it is the same. It's just that one we are looking at it in terms of kg, the other one we look at them in terms of mole. That's all. Okay, so now UH, Cv, and Cp depends on temperature only. So while we are on this topic, all ideal gases properties are actually dependent on temperature only. Unlike water, so like meaning when we're dealing with water R134, I always say that you need two properties, right? You need two properties, then you can find the other properties. For ideal gases, usually we only need temperature. That's the only thing that decide their properties. So for small temperature interval, we can, so the specific heat, okay, so rephrase again. So here we are saying that UH, Cv, and Cp depends on temperature only. So if the temperature interval is very small, we can use the average Cp or Cv value. So the relationship is actually not exactly a linear one, it's actually a curve lah. But if the difference is not very big, okay, so the interval here, we are not saying that anything under 200 degrees Celsius you can use average. We are saying that if the difference between 1 and 2 is less than 200, you can just average it. So for example, so we come back to this table. This table shows at 300 Kelvin, so it's just a fixed value, right? But if you go down to this table, so for A, you can see that at different temperature, it gives you different Cp and different Cv, right? So if you are asked to use average, so again, this depends on the question one. Question will tell you different, they will have different requirements, so you follow the question. So let's say if the question says that you need to use the average Cp, then yeah, you see. So let's say between 500 and 550, then you just find the average for the Cp. That's all. So you can see here we have Cp and Cv for different gases at different temperature. So this is one way to find out the Cp or Cv value. Okay, so at low pressures, all real gases approach ideal gas behavior, and therefore their specific heats depend on temperature only. So the specific heats of real gas at low pressures are called ideal gas specific heats or zero pressure specific heats, and are often denoted as Cp0 and Cv0. This one, just for your information, not too important. We rarely use this kind of thing. Okay, so here you can see that, yeah, in both cases, so this is what I said just now. The relation delta U equals to Cv delta T is valid for any kind of process, not just constant volume. Okay, so let's say here you see you have a rigid tank. So obviously you can use Cv delta T to find the change in U. So here, let's say if you have a constant pressure compression, let's say, but you only want the change in internal energy, you don't want the change in enthalpy, you can still use Cv delta T. So this relation is valid for any process, not just constant volume. So Cp also same thing. Okay, so here we will look at how we can, basically here we look at different methods of looking for internal energy and enthalpy for ideal gases. Okay, so this one again, this is for ideal gases. So just now we learned that we can use Cp delta T for enthalpy change and Cv delta T for internal energy, right? So you see, based on this example, this slide here, you should be able to notice that using CP delta T or CV delta T actually won't give you the exact value because we do have approximation here. Since CP and CV change with temperature depending on the process. So when we are looking for internal energy and enthalpy for ideal gas, we actually have three methods. So the first method is using tabulated U and H data. The second method is by using specific heat equation and perform integration. This one is very accurate but very tedious. The third one is to use the average specific heat, which is what you were shown just now. Actually, there's a fourth method, which is what we usually do. A very lazy method. We just choose constant specific heat at room temperature. So we don't care what temperature we are dealing with. We use a constant specific heat value. This will be the most not accurate one, but that's usually what we do because it's easier. We don't need to care what specific heat value that we use. We just use the value from A to. But we are not here to learn that for now. So we skip the fourth method. We look at the first three. Okay, so the first method is actually tabulated U and H data. This method is actually is the most accurate one because it is a how should I say? Because it is the method where we get value from the table directly. Stop scrolling. So in your table, if you go to a table A17, okay, yeah, here. So you can see that we have a table for ideal gas properties for air. So, and we mentioned that for ideal gas, properties are dependent on temperature, right? So you can see, you just need the temperature in Kelvin. So this one, the table is in Kelvin. So you can see that as long as you know what's the temperature, you can get the H, you can get the U. So one interesting fact that I can show you, which we don't really use it in our syllabus because it will get a bit confusing, is that you can actually notice that at low temperature, H is actually approximately temperature value. Can you see that? You can see that at low temperature, they are approximately the same value. But as temperature increases, so you can look over this side, when it goes to too high temperature, then it starts the difference starts to be very big. Like there's significant difference lah. So sometimes in some syllabus, right, they will actually tell you that no, at low temperature you can just assume T is H or H is T. That's why you can see that when we look at CP delta T, CP value is like 1.005. But I don't encourage this because, or I don't use this because we don't have a fixed definition of how low temperature is low. So we don't know like at what point you can't use this relation anymore. So I don't really encourage that. If you have the table, just use the table. But again, it depends on the question. Okay, so that is the first method. So first method, you just use the table. Go to the table, you can find the H and the U value. If the temperature is in between, then same like the water table, you interpolate. That's all. Second method is the one that students would like, which is also a bit more troublesome. We'll come back here. I won't show too much lah, this one. But you still need to learn. So just now we showed that we have a table for all the temperature, right? So you go down, table A2. So you have another equation. You have an equation here that shows you the CP value, and you need to integrate this equation to get the CP value. So meaning, let's say you have air, right? So you sub in 28.11 to A, you sub in this value to B, you sub in this value to C, you sub in this value to D, then you integrate this whole thing, then you will get the CP value. So a bit more maths lah if you use this method. I will show you in the subsequent example later. Okay, so here we have these three methods. So the third method, we have talked about it. So in the following example, you will see that we use all three methods to show you the answer. Okay, So air at 300 Kelvin and 200 kilopascal is heated at constant pressure to 600 Kelvin. Determine the change in internal energy of air per unit mass. So A by using table A17, B to use the equation that I showed you just now, and C we use average specific heat. So assumption here is A is ideal gas. So part A is the easiest or the most straightforward method, and also the most accurate. So the only issue is you need this table basically. Yeah, if you don't have access to this table, then B and C will be your method. So one way of determining the change in internal energy of air is to read the U value at T1 and T2 from table A17 and take the difference. So that's all. So just the table that I showed you just now, get the U value for 300 Kelvin, get the U value for 600 Kelvin, minus them off, then you get the change in internal energy. So this one very straightforward. I won't discuss too much here lah. So you can note that the value is 220.71 because we will do a comparison later. So method B, so like I said, you use this equation. Then you need to sub in the A value, B value, C value, D value. But this equation, the issue is that it is a CP equation. We are looking for internal energy here. So we want CV. So you can see that this equation actually is in terms of bar. So we can minus RU here. Basically we use the CP equation to minus RU, which is the universal gas constant. Then you will get a CV counterpart. So from here, you integrate this entire thing with respect to temperature. So T1 to T2, you will get the U value directly. Because when you integrate it, it is basically CV delta T, right? So you will get delta U, but this will be in terms of kilomole. Then yeah, you need a bit of chemistry, then you need to divide by the molar mass of air, which is 88.97. Okay, so this one also, you most probably won't need to use this, but just for your information lah. Molar mass, pretty sure no one will remember most of them, right? You probably remember, but you should at least know like carbon is 12 lah, that kind of thing. Actually, molar mass is given here, but in the exact value, in the first page. So, but this will be the exact value lah. For you, most of the time, things like air, you will use 29. You should actually round up in most cases. Okay, so like carbon dioxide is 44 usually, monoxide 28, that kind of thing. But it's given here lah if you need to. But most of the time, I won't ask you to use this method one. But you still need to know the integration is actually not hard because it's just t squared and t cubed. Just need to submit the value. Okay, so this way, if you solve this, you will get U bar. You divide by molar mass, you get delta U value. So this delta U value is 222.5 compared to the previous page where you get 220.71. So the difference you can see actually is not that big. It's only about 0.8%. So that's why we say this method is a very accurate method. Now we look at third method. Third method also very straightforward. We want the average CV value. So you find the average temperature, 450 Kelvin. Then you look at what is the CV at 450. You can also find the CV at 300 and 600, then average lah. You will get the same thing also. Okay, then you use this new CV value, you find CV delta T. So this gives you 220. So this is actually quite close to the tabulated value as well, because the tabulated value is 220.71. So it's actually very, very close. So like I said, this method is actually quite close. That's why sometimes instead of looking for the table, we will just do the calculation because it's faster. So this close agreement is not surprising since assumption that CV varies linearly with temperature is a reasonable one at intervals of a few hundred degrees. So here the difference is 200. Just now we mentioned 200 difference. So even at 300, the value is still quite accurate. So if we had used the CV value at T1 equals to 300 Kelvin instead of T average, I'm talking about here. This is what we usually do. This is what I said just now. So, okay, what we usually do is actually this, because we got lazy. Then the result would be 215.4. You get 2% error, still acceptable. That's why, yeah, then we don't go through all the trouble to find all this average. We just use the room temperature value, which is at 300 Kelvin. Okay, so clear so far? So now I just show you all three methods of looking for the change in internal energy. Okay, so now we actually have two last examples. Let me see what is the other one first. Okay, so we have two last examples before we can close up this chapter. This one I let you do, the other one I will discuss. So now we just look at this first. I'll read the question first. So an insulated rigid tank initially contains 0.7 kg of helium. So we're dealing with helium here at 27 degrees Celsius and 350 kilopascal. A paddle wheel with a power rating of 0.015 kilowatts is operated within the tank for 30 minutes. Determine the final temperature and final pressure. So you try this out. Essentially, you are dealing this question. You are trying to solve this question based on just the closed system method that you learned. Just that now we are dealing with ideal gas, which is a helium instead of water. So the method will be quite similar, except that now you change the entire reading table method to using ideal gas equation and Cv delta T. Okay, try this out. And I'll give you about 15 minutes. Try this out. Then yeah, whoever want to have a break, you can also have a break. This one.